All right, welcome back. My goal is to wrap up this chapter in this video here. So this is section 9.9, talking about different trends in the periodic table. And the way the periodic table is organized, there's actually going to be some trends that you may have already been picking up on this year as we've been looking at the periodic table and doing things with it. But now that we've learned about electron configurations and what those electron configurations look like as you keep adding electrons and going through the periodic table, then you should be able to really understand some of these trends a little bit more. And so there's going to be three trends that we look at that you're going to be able to use a periodic table to answer questions like which atom is bigger. So we're going to look at atomic size. That's going to be one of the trends that shows up. And it all has to do with electron configurations. Okay, you might be able to answer questions like which element has a higher electron affinity, or which element is more hungry for electrons, sodium or magnesium or whatever. You might say neither one of them. They want to lose their electrons. Well, true. Well, there's a term we use called ionization energy, and that has to do with how much energy it takes to pull an electron away from an atom. And so we'll look at that and the trends that are associated with that term on the periodic table. The third thing that we'll look at is metallic character, which has nothing to do, by the way, with how shiny something is. It's in reference to something else. In fact, what I just mentioned, you know how metals like to lose electrons? That's basically it. And so you can look at a periodic table and see which element is more eager to lose an electron. But there's some factors that you'll see that we need to consider in terms of electron arrangements. So these are the three trends we're going to look at: atomic size, ionization energy, and metallic character. So without any more to say on that, let's just jump right in. So where was I? Oh, here we are. So the atomic size of an atom is real important, and it's determined by the distance between the outermost electrons and the nucleus. Okay, and so you'll see something very interesting happen here. As you move across the periodic table, you know that electrons are going to occupy orbitals with the same principal quantum number, right? Since the principal quantum number largely determines the size of an orbital, electrons are therefore filling orbitals of approximately the same size. So you would think that the atomic size would remain relatively constant or get bigger. Some students will think it gets bigger, but you're filling the same principal subshell. So you're basically just adding little orbitals in different planes, but you're kind of staying in the same principal subshell. So as you add electrons across the row, shouldn't be getting too much bigger. Should be kind of remaining the same size, but students will think they get bigger. But the last thing that you would think of is that the atom would get smaller, but that's actually what happens. And so check this out. What actually happens is, as you keep adding electrons when you're going across, you're also adding protons. Okay, the difference between lithium and beryllium is not just an extra electron, it's an extra proton as well. And so as you keep adding protons and electrons together, but yet you're adding electrons to kind of the same energy level, you're adding more strength to the nucleus by adding protons, because remember, opposite charges attract. So as you add protons to the nucleus and you go across, you're able to pull those electrons in a little bit closer. In your book, just horrible job, didn't even show you that. So just Google atomic size, I don't know, illustration, and you'll probably find something really good. Okay, the way it works, well, definitely you'll find a lot of these tables that will quickly give you an answer. Like if I give you this table here, all I'm going to do is on the test, I'll ask you, which is larger, bromine or potassium? And so you'll just look here and you say, well, potassium. So these are pretty easy questions to answer, but I want you to understand the why as well, because it's very counterintuitive, and a lot of students will make the wrong mistake if they don't do this right. Why? How about this? Why does atomic size decrease across a period? Here you go. Here's a nice little illustration. So you see here, if we go from lithium to beryllium, hey, that's what we were talking about, wasn't it? You're going from 3 protons to, oh, wait, what? To 4 protons, but they have 4 protons in both these examples. Ugh. You can't always trust Google, right, guys? But let's just stick with this analogy here. Watch. What you can see here is that the radius is going to decrease from the nucleus to the orbits. From the nucleus to the orbits, this gets smaller, doesn't it? This distance gets smaller. So if you were to look at the diameter, if you would, or the radius, it's going to decrease. It's going to shorten. This atom is smaller than this atom. But what you have to consider is that there's only 3 protons here instead of 4. So just pretend there's only 3 protons there. Here, I'll put my cursor over that proton so you can't see it. So the lithium atom only has 3 protons. Well, that's only so strong, even if you give it 4 electrons. But if you give it another proton and having 4 electrons, because these protons are positively charged, they pull on these electrons closer to the nucleus, right? It's like you're giving more muscle to the nucleus, so it's going to pull those electrons in tighter, all right? So basically, that has to do with ionization energy. We don't want to go there yet. We'll eventually get to that. But yeah, I don't know why there's not a good image of this. But essentially, lithium has 3 positively protons. Well, that's not that strong, so it's only going to pull the electrons in so tight. But beryllium has 4. It's going to pull them in even tighter. Boron has 5 protons, so it's going to pull the electrons even in tighter. Carbon has 6 protons, so it's going to pull the electrons in even closer, right? Because the positively charged protons are just adding more strength to the attraction. Because remember, positively charged protons are attracted to the negatively charged electrons. Now you might be asking yourself, but wait a minute. If the electrons are attracted to the protons, why don't they, in all 4 of these examples, just go and just get sucked into the nucleus like gravity? Why doesn't the positively charged protons, like a magnet, just pull the electrons in? Well, it's because the electrons have kinetic energy. It's because they have kinetic energy, so they're wanting to leave, but yet the protons are keeping them there, just like our planets would like to leave our solar system, but yet the sun is pulling them closer in. So it has to do with the electrons having energy. They're zipping around the nucleus, but they're not really. They're essentially like just energy in the form of a wave around the nucleus, right? So okay, so the point is, the positive amount of energy, the extra positive protons you're giving, can pull those electrons in closer, so the atoms get smaller. But now check this out. As you go and add a new energy level, let's say you're in row 2, the second principal shell, and let's say you jump down to the 3s. Well, all of a sudden you just added a new shell, and so it's going to get quite larger. If you watch that animation video I showed you in the last lecture, you can see it. The 3s takes up just basically shields the round 3s structure. The round 3s orbital overpowers and covers up everything that was below it. And then the 3p orbitals, they kind of merge, or I figured out what that word is in the last lecture. I couldn't remember what the word is. Like I said, I was saying that the orbitals will merge or fuse together, or it's called hybridization. It's called orbital hybridization. So the s orbitals and the p orbitals will kind of hybridize to form kind of a hybrid shape. But yeah, we're not going to go into like all that. Basically, I just need you guys to understand that orbitals have shapes. They do hybridize, but also that you mostly know how to fill those orbitals and such. And also know that those orbitals get larger as you go from 3 to 4 or 4 to 5 or 5 to 6. Those s orbitals, the spherical s orbitals are larger, and so are the dumbbell shaped p orbitals, which are not really shown here. They just show it all as round. They're just trying to make this simple. This is kind of a comparison chart. So this is a chart you would use that shows the relative atomic sizes of the main group elements. Notice they've left out the transition metals. So they're just showing column 1 and 2, leaving out the transition metals, and then showing columns 3 through 8, or 13 through 18, however you want to call it. If you call it 3 through 8, you need to say 3A through 8A. But okay. So, and that's because the transition metals, they kind of just stay the same size. They don't really change size too much. And they do some kind of weird stuff with their electrons and the d orbitals that I don't want to get too far into actually with this chapter. So, what's the difference between carbon and oxygen? Which one's larger is what this question is asking. Carbon, oxygen. You can kind of tell just by looking at it. You can see the progression. Carbon's going to be bigger. If you were to just look at this and just look at that, you may not be able to tell. What about lithium or potassium? You can totally tell right there, right? As you go down in energy level, you're totally getting larger, even though you're staying in the same column. Calcium or aluminum. Here we have calcium. Where's aluminum? Right here. Oh, this one's interesting. So notice that as you go down an orbital, or as you go down a principal number, you're obviously getting bigger. But as you go left, you're also getting bigger. So we're getting bigger two different directions, aren't we? And what about selenium or iodine? Here's selenium, here's iodine. Again, this is a diagonal movement. So we're going down a row, which means we're adding a new shell. So if we're going from the 4th shell to the 5th shell, we're definitely getting larger. But we're moving over to the right. So that means we're getting smaller. So what really happens? Going down makes us go larger, but going to the right makes us go smaller. And so they kind of cancel each other out, really. So that's actually the answer to this question. Since one trend makes it increase and one trend makes it decrease, they essentially cancel each other out. So do Skill Builder 9.6 as some practice if you want, or you can jump straight to the homework problems I assigned you. I think I gave you a few on atomic size. Let's look at ionization energy. This one's quite simple as well. Ionization energy is the energy that is required in order to remove an electron from the atom in the gaseous state. So kind of some specifics there, but in general, let's just think about it like this. It's the energy that's required to remove an electron, one electron. So for example, the ionization energy of sodium can be represented like this. You have some elemental sodium, which we know is very reactive. You just put it in water and it's going to like explode. So elemental sodium is a metal that's not to be played with, and you must respect it because it has a low amount of ionization energy. It does not take up very much energy to remove its electron. In fact, sodium is begging for you to take its electron. So the amount of ionization energy is very low, but you still have to have some. You have to have some energy to remove the electron, and when you do, here's your product. You have a sodium ion and a free-floating electron that you can donate to, say, I don't know, chlorine or some other atom that would like to gain an electron. And so based on electron configurations, what would you predict about the ionization energy trends? Would it take more or less energy to remove an electron from sodium than from chlorine? Well, we just said it didn't take very much sodium or energy to remove sodium's electron. Well, what about chlorine? Chlorine's begging to gain an electron. So the last thing you're going to do is steal an electron from chlorine. All right? So sodium is like the guy on the street just begging for you to come take something from him. Chlorine is like the guy on the street that's like trying to get money from you by hustling. And you're not about to give up something. He's trying to hustle something from you. So if you're looking at the ionization energy for chlorine, it's going to be really high. It's possible. It's quite possible, but the amount of energy required to take an electron away from chlorine is really high because it's traditionally going to gain an electron. If anything, it's going to take an electron from you. All right, so watch out for chlorine. But sodium, it doesn't take any energy. I shouldn't say any, but it takes a low amount of energy. I'm being facetious. Okay, so since moving an electron, or since that's the case, here's the trend. As you move across a period, so as you go from left to the right in the periodic table, ionization energy increases, right? So you can look at a periodic table like this, and you know what? I don't think the book did this, did they? Oh, yeah, this made me so mad that the book didn't do this. Oh. So I gotta go to Google again, but just real quick, let's look at this periodic table. As you go from left to right, ionization energy increases. Again, everything in this column is just begging you to take an electron away. And so it's really easy. It doesn't take much energy to take an electron away. But as you go further and further down here, these elements are finally, like chlorine, bromine, and fluorine, they're eagerly trying to gain one electron to be like the noble gases, so that they have 8 valence electrons. And so that's going to require a ton of energy to take away their electrons. In fact, they don't do it. They don't even give them away. But it is possible with the right amount of energy. It's like possible theoretically. So there is a number associated with it. And that's what I wanted to show you in just a second. But first, let me address the y-axis. As you go down the periods, which are another name for rows in the periodic table, as you go down the rows, what happens? What's the trend? Well, check this out. This is interesting. Cesium is way more reactive than sodium. So we said that sodium was reactive, and so is lithium, by the way. You put lithium in water and it'll react. Sodium catches fire. Potassium blows up. Rubidium blows up even more. Cesium, it's like dynamite. Francium is like so unstable it doesn't even exist. So you get more unstable as you go down. And here's why. These electrons in cesium are way out on energy shell number 6. So any protons that have the ability to hold on to that electron are way in the center, while the free-floating electron, the one valence electron in the outermost shell, is way out here. So it's real easy to take it away because it's not near the protons. So think about it like this. You have protons in the middle. They're like your parents trying to hold you in, keep you close. And you're in energy shell 1 or 2. You're pretty close to your parents. It's going to be pretty hard for someone to take you away. All right. But if your parents are close here and you're in electron shell number 7 or electron shell number 8, way far away from the nucleus or your parents, it doesn't take much energy for someone to snatch you away. That's why you want to stay close to your parents, right? Even as you're older, stay close to your parents because they're protecting you. Okay, they have the power, the force, the attraction. Okay, you notice kids, they're attracted to their parents because they feel safe and secure. So they want to be close to their parents. So that's just an analogy I'm using. But it has to do with the cesium and the francium's electrons being way far away from the nucleus. The farther you get from the nucleus, the easier it is to take that electron away. Because, remember, it's the nucleus that's positively charged. If the nucleus is positively charged and the electron is negatively charged, that's what's creating the attraction. So the farther that electron gets, the less attraction there is, right? You take 2 magnets and put them far away from each other and there's not really an attraction. It's pretty easy to pick one up. Put the 2 magnets really close to each other and it's going to be hard to move one or the other because they're going to be attracted to each other. All right, so that's the trend. I did want to show you that there are actual numbers associated with that. And so that's really the way we should be studying this. ionization energy chart or ionization energy periodic table. And I don't mind if you look at these too, by the way, when you're solving the problems that I give you. It's basically a table like this, but it gives you numbers. Well, this just gives you arrows for a trend. Ionization energy increases as you go up, and it increases as you go across. But there's also, I personally find it easier to look at the 3D ones. Check this out. This is really cool. You guys will like this. And there's these 3D tables for all of them. I love these. So this is the ionization energy trend periodic table. So notice, again, it doesn't take a lot of energy for francium to take its electron away. It's begging you to take its electron away. Chlorine, it's going to be real hard. It's going to be even harder for fluorine. Good luck ever trying to get an electron from helium. That looks like it's just not going to happen. So, in fact, it's been said that if you ignore the noble gases, because they obviously have really high ionization energies, that the most electronegative element is fluorine. So the most reactive of the elements is fluorine, because it's just begging to gain an electron. It just needs one electron, and it can be just like neon. So fluorine is super reactive. Fluorine gas is very, very reactive and dangerous. Likewise, cesium is really reactive because it wants to lose an electron really bad, because it's way out on those outer shells and there's hardly any attraction to the nucleus. So the amount of energy is really low. So guess what? If you put cesium anywhere near fluorine, you pretty much have a spontaneous reaction, don't you? So I kind of like these 3D charts like this. They're really neat. As you can kind of see, I have a lab I do with straws, and you guys cut straws based on these numbers. So like the numbers are like in volts, or they're in kilojoules per moles, I'm sorry. So it takes 1681 kilojoules per mole to remove an electron from fluorine. It takes 376 kilojoules of energy per mole of cesium to remove an electron. So I could totally ask you guys, like, how much energy does it take to remove so many electrons from so much cesium? And you could totally use dimensional analysis and stoichiometry to figure that out, but not trying to go there with this chapter, so sorry. Again, and this is called the first ionization energy. It has to do with removing that first electron from an atom, also in its gaseous state. So that's kind of important as well. So, but just forget that definition. Just know the trend, okay? You guys are good? All right, let's move on to the third final trend. Periodic table trend referring to metallic character. Actually, we didn't do any examples, did we, with ionization energy? Do we need to? Yeah, let's do it. Magnesium or phosphorus? Well, here's magnesium. Where's phosphorus? Over here. So we're scrolling right until we get to phosphorus. Well, if you scroll right, what happens? The energy increases. The energy increases, so choose the element with the higher ionization energy. Well, then it would be phosphorus, right? How about silver or antimony? Silver is right here, Ag. Antimony is right here, Sb. Again, I'm scrolling to the right, so it increases. So Sb is going to have the higher ionization energy. How about nitrogen or silicon? Well, nitrogen is right here, and silicon is down and to the left. So we're moving diagonally. What's going to happen here? Well, let's see. If we move down, the ionization energy decreases. If we move to the left, it also decreases, doesn't it? So we're decreasing both directions. So decreases, that means that nitrogen is going to be the winner by having the highest ionization energy. You guys get the point. So we don't need to do too many examples there. How about metallic character? Again, I like this periodic table because it's kind of like this one up here, but yet it's got arrows. They're just going to say different things. That's all. But let's first talk about what metallic character is. So this is kind of weird. I'm not going to lie. Metallic character has nothing to do with how shiny or how sharp or whatever you would typically think of a metal. The definition of a metal here is going to have to do with all these elements to the left of this little staircase. The staircase that separates the non-metals and the metals is there. And remember, those are kind of like metalloids. Sometimes they're like metals and sometimes they're like non-metals. So they kind of act like both. Sometimes those are called semi-metals and they're like semiconductors. One property of metals is that they're conductive. And something like silicon, which is a semi-metal or semiconductor, it'll sometimes transmit electricity and sometimes not. So you can almost make it like a switch, where sometimes it's moving electrons and sometimes it's not. And that's how we have circuit boards in our phones and stuff like that. But other metals, like over here, they're constantly wanting to lose electrons, and it's pretty easy for electrons to flow through a bunch of atoms if you have them all like right by each other, side by side. So electrons are wanting to leave metals. Like that's kind of the key to a metal, is that they like to lose electrons. There's actually a term for that. It's called oxidation. If you remember the mnemonic oil rig, oxidation is losing electrons and reduction is gaining. Metals get oxidized. Okay? Metals get oxidized. That means they like to lose electrons. When copper, like on the Statue of Liberty, there's Cu, copper. When it gets oxidized, it turns green. When iron oxidizes, it turns into rust, which is orange. And so all metals like to be oxidized. When sodium get oxidized, which that can just happen in water, it likes to catch fire. Or most of these metals, actually, if they're oxidized in air, they just kind of turn white. So like, I think one time I had to try to do a lab with you guys on, we were looking at the reactivity of metals, and I tried to use some, what was it, zinc? I think it was zinc, yeah. And it was all oxidized. All the zinc had like a white film on it. And so basically I didn't really have any pure zinc. It was all had already been oxidized. Or no, it was calcium. It was calcium. So calcium, I was going to say zinc, that doesn't oxidize very well. Zinc, though, does. So this is leading me to my point here. You see how calcium is way far to the left here? That means it likes to lose electrons really easily. And so does potassium. Potassium likes to lose electrons, therefore it's metallic. So basically, and I kind of think this is stupid, to be honest with you, like metallic character is the same thing as well, it's the opposite of ionization energy. It's the opposite of ionization energy. So let's just pick a really, really reactive element, like cesium. Cesium has that electron really, 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 really far out on its 6th energy level. Let's say francium, the most extreme. Francium's lone valence electron is way out on the 7th energy level. So it's really easy to take it away. So the ionization energy is low. That's what makes francium reactive. But since its ionization energy is low, its metallic character is high. Francium is the most metallic metal. Does that make sense? Cesium is a little bit less metallic, but it's pretty metallic. It's pretty metallic in the fact that it easily wants to lose that electron. So it's just the opposite of ionization energy. Okay? And we can prove that. Let's see. Metallic character, it decreases. Metallic character increases as you go down. For ionization energy, it decreases as you go down. For metallic character, it decreases as you go to the right, but it increases as you go to the right for ionization energy. So they're just opposite to each other. But so what's more metallic, oxygen or nitrogen? You might say neither one of them's a metal. Well, yeah, neither one of them are a metal, but you can still talk about them in terms of their metallic character. Well, if one of them was gonna be more metallic than the other one, it would be the nitrogen, right? Because it's closer to the left. Okay, all your metals from the left of this stair step are definitely going to lose electrons. That's a guarantee. The further left you are, the easier it is to lose those electrons because you only have like one. In fact, in column 1, there's literally only one valence electron. Column 2, there's 2 valence electrons. Transition metals, it kind of depends. It depends on what non-metal they're with. Speaking of non-metals, now that we're over here, these non-metals, they don't lose electrons. They gain electrons. But still, we can, we can still say that they just don't have any metallic character. In fact, let's see if there's a 3D chart. I'm curious what that looks like. Periodic table 3D, we'll say metallic character. And honestly, ionization energy is the one that professionalists use. It's way more professional. We don't really talk about metallic character, to be honest with you. I probably should have skipped it. Ionization energy is the more important one. In fact, they should have left out metallic character and talked about electronegativity. Electronegativity is really, really important. And it's the opposite of ionization energy. It's the opposite of ionization energy, and it's how hungry something is for an electron. So elements, actually, it's the opposite, but as far as values go, if ionization energy increases, then the electronegativity decreases. Wait, no. It's in the same direction. Ionization and electronegativity, they both increase in the same direction, but they don't mean the same thing. In fact, they mean the opposite thing. Electronegativity, the higher the number, the more hungry something is for an electron. So that's how much something wants to gain an electron. So fluorine is the most electronegative element. It's the element that's most hungry for an electron. So I don't even know why the book didn't talk about that. But if something has a high ionization energy, that means it takes a lot of energy to take its electron away. So it means it's probably not going to happen. So even though ionization and energy and electronegativity both increase as you go to the right, they actually mean the opposite. They actually kind of mean the opposite thing. All right, so this is kind of a neat little table because it shows everything there in one. But as far as size goes, like atomic radius, it's a whole lot easier to look at one that actually shows you the literal sizes of the element. But you can find them with numbers. You can find them with atomic size, periodic table with numbers. So atomic size values. Check this out. This is the one I usually pass out in class. See how the transition metals kind of look the same? They don't really change size too much. This one is not the one, I guess. They don't really have a value. I mean, the value is like really small anyway. It's like the atomic radius. So it's in like nanometers, right? So 0.111 nanometers is the atomic radius for beryllium. So we're talking like nanotechnology here, like super small increments and measurements. Nanometers. Nano means times 10 to the negative 9. But that's the kind of measurements we deal with in nanotechnology. So when they're making circuit boards with silicon, like we were talking about in your cell phone, they're making circuit boards with particles to the times 10 to the 9th power. So their circuit boards so small you can't even see the circuits. All right, that's it. Let's. You want to try an example real quick? If you want to stop this, you can and do your own work. Otherwise, you can look at an example with me. Tin or what was that? Tellurium. I'm getting delirious right now. It's getting late. Tin or tellurium. Well, if tin is here and tellurium's here, I know that metallic character basically starts to drop off as you go to the right. You become less metallic. Eventually, you're going to be over here in the non-metals. So I'm going to say that tin is the answer. Silicon or tin? Well, silicon is up here and tin is down here. So what happens as you go down? We said going to the left makes you more metallic. What about going down? Going down also makes you more metallic too, because those electrons are way far away and they're easily removed. So those metals become very reactive. Metals down here are very reactive. So as you go down, that would make tin more metallic than silicon. And you should know that just from the fact that silicon is not really a metal. It's a metalloid. What about beryllium or tellurium? Well, tellurium is more metallic. No, I'm sorry, bromine. Excuse me. I was like, what? Bromine or tellurium. Tellurium is actually going to be more metallic. And you should know that because bromine is a non-metal. And tellurium is still one of those metalloids. But if you don't want to know it that way, know that you're getting closer to the metals as you go left. So the fact that we went left means we're going closer to the metals. But the fact that we went down to become tellurium, to go from bromine to tellurium, we went down a row. That means that you're on a whole nother level. Literally. The electrons are on a whole nother outer level, so it becomes more metallic. Selenium or iodine. Well, this one's tricky. These are the tricky examples because guess what? As we go down, we become more metallic. But as we go over to the right, we become less metallic because we start heading into the nonmetals. And so, really those trends just tend to cancel each other out. So that's kind of how you would answer that question. All right, that is it, guys. We just did all of chapter 9, and we still have like all of this week and the next and the next. So I'm going to start giving you guys chapter 10 videos pretty soon so that you can start doing electron dot diagrams. Those are kind of fun, and they require a little time and work, so we'll get that coming your way ASAP. But thanks for watching this one. Bye-bye.